everybody. Welcome back to the second semester. I hope you guys had a good weekend. We're going to begin chapter 6 in geometry, all about polygons. And today we're going to be looking at just some vocabulary and then also how to find the sum of the interior measures of a convex polygon. So first we're going to take a look at some definitions. So you might want to get your notebook out, maybe even pause the video, write down some of these definitions. But first of all, the definition of a polygon is a closed figure, so no openness like this, formed by line segments so that each segment intersects exactly two others, but only at their endpoints. So right here, even though they intersect each other, they have to intersect at their endpoints, okay? So right here, this is open. Right here, this is not a segment, it's curved. And so it has to be endpoint to endpoint, closed figure in space, endpoint to endpoint, okay? So these are polygons. Over here on the left is not any polygons, all right? Next is convex versus concave polygons. Convex has no diagonal with points outside. So if you were to connect all the diagonals of all the vertices, none of the diagonals would be outside. Also, each angle measures in a polygon measures less than 180 degrees. Okay, right here, if you connect any of my diagonals here, some of the diagonals lie outside my polygon, and that is a problem. Okay, or I should say less than 360 degrees up here. Sorry about that. So right here, identify polygons that are concave or convex. And so this one right here is convex. Oops, here we go. Convex. Oh no, I don't have my pen. Here we go. Convex. This one kind of caves in on itself, so it's concave. And also you can tell because if we were to connect these vertices right here, it would give us a diagonal outside. This is not even a polygon. Okay, so not even a polygon. This is I should call this a polygon, sorry. Polygon. Polygon. This right here is a concave polygon. Okay, it connects right here. So this diagonal right here would connect outside the polygon. And this one right here is a convex polygon. Not writing very good. My pen is not doing very good lately. I don't know what the problem is. Okay. Okay, then we have lots of definitions here. So I'm sure you know what a lot of these are. You might not need to take notes on some of them you might. If all the sides are the same length in a polygon, it's called a regular polygon. Okay, so all the sides will be the same. All the angles will be equal measure. If they're not the same length and the angles are not the same measure, it's called an irregular polygon. Okay, 3 sides is called a triangle. 4 is a quadrilateral, 5 is a pentagon, 6 is a hexagon, 7 is a heptagon, 8 is an octagon, 9 is a nonagon. I always like to think like a nonagon, and 10 is a decagon. Okay, we'll kind of get up as far as there. 11 is a undecagon, and a 12 is a dodecagon. It's like uno and dos for Latin words we usually take in Spanish. Okay. Then we have all kinds of special polygons. So first we have triangles, and you should be familiar with these. A right triangle, an acute triangle, a scalene triangle, equilateral triangle. And then each of those are isosceles. We have right isosceles, obtuse isosceles, and so forth. Okay. Then we have special quadrilaterals. We have a rectangle, which has 4 right angles and 2 opposite sides that are equal. A parallelogram has 2 opposite sides that are equal, but not right angles, has opposite angles that are equal. But a rectangle is a parallelogram, but not the other way around. Okay, so no converse statement there. A square is a rectangle and a parallelogram because it has opposite angles that are equal and parallel and all right angles. And a rhombus is a parallelogram, but not a square. Okay, a square is actually also a rhombus. Okay, so a square is special. It's a rhombus and a parallelogram and a rectangle because it meets all those criteria. Okay. A trapezoid has 1 set of parallel sides, right? Let's see, and those sides are opposite. Isosceles trapezoid is kind of like an isosceles triangle with its head cut off, right? So 2 parallel sides, the base angles are equal, and the 2 sides are equal. A kite is like 2 isosceles triangles sitting butt to butt. So we have like a little isosceles triangle here and a different isosceles triangle here. So they can't be the same. Otherwise, that would be a rhombus. Okay. So they're different sides congruent there. Okay, so this is like a little polygon tree, a geometry, where we have our triangles and equilateral, right, isosceles, and scalene triangles. Okay, we have quadrilaterals, we have trapezoids and parallelograms that are both quadrilaterals. And from the parallelograms, we have rectangles and rhombuses that are both squares. And then we have pentagons, hexagons, octagons, 9-agons, 10-agons, 11-agons, 12-agons, and so forth. Okay. So now we're going to get into interior sums of angles, right? So right now, if I were to take this triangle, you all should know that the sum of the angles in a triangle is, hopefully I can hear you right now, 180 degrees, right? And there's 3 sides to my triangle. Well, if I take my quadrilateral here and I divide it, so I go from one vertex here to my other vertex, I can create 2 triangles here, right? So I can create these 2 triangles, and each one of these would have 180 degrees here. I don't know why it's not writing. There we go. And 180 degrees here. We have 2 triangles, right? So we make, this has 4 sides and 2 triangles, okay? I can do the same thing to this pentagon. I'm gonna grab it my little side over here again. If I go from one vertex here, boom, and I go over here to the same vertex like this, notice I can make 3 triangles, okay? So if I have 5 sides, I can make 3 triangles. 1, 2, 3. 180, 180, 180. Okay. And if I add all those together, that tells me my sum of my interior angles. So here's a little chart for you on the next page. So if I have my triangle, had 3 sides, 1 triangle, of course, and then so we take 1 triangle and multiply by 180 gives me 180. If I had that quadrilateral, right here, I made 2 triangles. I can take those 2 triangles and multiply by 180 to get me 360 degrees. So a quadrilateral has a sum of 360 degrees of the angles, okay? We can take my pentagon like we did on the previous page and divide it into 3 triangles. So 5 sides gets 3 triangles. So I take those 3 triangles, multiply it by 180 degrees, gives me 540 degrees. Okay, so you'll notice each one of these increase by 180 each time. Up by 180, up by 180, up by 180, etc., because we're adding a triangle basically every time, okay? And so you'll notice that each of these right here, I have, get a different color here, I have 2 less, I'm going to say 2 less. The number is 2 less, the number of triangles is 2 less than the number of sides. 2 less than the number of sides. So now I know that my number of triangles with some n, it's like, I don't know, maybe it's 100 sides, I don't know. N sides, that means it's going to have the number of sides minus 2 for the number of triangles. So then we have this beautiful formula of n minus 2 that will give us a number of triangles we have times 180 degrees. So that is my formula for the interior angles of a triangle, okay? So don't pay attention to this yet, okay, because we're not going to get there just yet. We're just paying attention to the interior angles for now. Okay, so n minus 2 times 180. Oh, I'm sorry. Actually, I need you to pay attention to this part over here. Don't pay attention to these parts. Okay, so right here. If I wanted each angle in a regular polygon, I'm going to take n minus 2 times 180 and divide it by the number of sides. And that will give me each angle. If I distribute this right here in 180 times n minus 360 over n, then I get this up here, which kind of makes sense because you can take 180 degrees and subtract all of the interior angles, and that's what you take. You're taking away. Here, I'll draw a picture. I go like this, right? If I want to get all of my interior angles right here, this is 180 degrees. So I take 180 degrees and minus each of these in there. Okay, 360 divided by n. Okay, so you can just remember how to do it this way, or you can remember this formula also. Okay, so now we're going to practice a little bit. How many triangles are formed by drawing the diagonals from the vertex of a convex octagon? So an octagon has 8 sides. So we would take 8 and minus 2, and it would give us 6 sides. Or no, 6 sides, 6 triangles. Okay, so 6 triangles. So then what is the interior angle sum for the convex octagon? We would take 6 triangles and multiply that by 180 degrees, right? So 6 times 180, gotta look at my calculator here, is 1,080 degrees for the sum of the interior angles of an octagon. And as you know, as it gets bigger and bigger and bigger, the sum is going to get bigger and bigger and bigger, okay? Jen is building a corner cabinet to fit in a rectangular room. If she builds it with the angles shown, how can she determine whether it will fit or not? Well, we want this to be 90 degrees, right? Because that's how it's going to fit in the corner of the room. We got to check and see if that's going to be 90 degrees. This is a 1, 2, 3, 4, 5-sided polygon. So a 5-sided polygon should be 5 minus 2 times 180 degrees. That's going to be 3 times 180 degrees, which is going to be 540. So that sum should be 540 degrees, okay? So now we're going to take each of these, and we're going to call this x, okay? So we're going to take x plus, we have 2 90 degrees, so I'm going to go 2 times 90, plus I'm going to go 2 times 135. That should equal 540. If that is indeed 90 degrees over there, okay? I'm going to get out my little trusty calculator right here, pop it up. Oh, it's a big calculator this time. I think they changed it on me. See, make it smaller. Nope, I can't. Okay, so I'm going to take x plus 180. 2 times 90 is 180. Plus 2 times 135, what is that? We'll go 2 times 135. Whoops. What? Gracious. 2 times, oh my goodness. Got a quiz. There we go. 2 times 135 is going to give us 270. Okay, so x plus, then we're going to go 270 plus 180, and that's 450. We're going to subtract 450. So x should be equal to 90 degrees. And there you go. So it will fit. Okay? So that's a little bit of application for our polygon sum theorem. So here's a tricky one. Each angle now of a regular n-gon measures 172.8. So how many sides does an n-gon have? Okay, so that's the one we had where we took 180 degrees minus our 360 over n. That should give us each individual measure, so 172.8. Okay, and so maybe keep that formula down close somewhere. Okay, so I'm going to subtract the 180. So negative 360 over n equals, I believe that is a, what is that, 7.2, negative 7.2. Now right here, you can write this as a fraction of 7.2 over 1, and then you could do your proportion rule, which is this times this equals that times that. Okay, so negative 360 times 1 is going to be negative 360 equals, we'll go like this, negative 7.2 times n equals negative 7.2 n. And now I can just solve for n. Divide by negative 7.2. Divide by negative 7.2. And I'm going to get n equals 5 on this. So that polygon is a 5-sided polygon, a pentagon. Okay? Okay, what is the interior angle sum of a 17-gon? So this is, we're going to use the sum formula. So n minus 2 times 180 degrees. So we're going to plug in 17 right here. So 17 minus 2 times 180. That will be 15 times 180. And what's 15 times 180? Is going to give us 2,700. That is a lot of angles. 2,700 degrees. Okay? All right. So you have an Excel in Google Classroom. This should say 6.1, not 5.1. I thought I changed that. So we're going to change that right now. So that should say 6.1 in Google Classroom. Be sure to attach all of your work and answers. There should be no blanks. There should be no not applicables. There should be no skipped answers and so forth. Okay, so you should be completely have just like you're doing it from the book. All of the numbers, should see them all numbered out. Okay, I hope you guys have a great week. I hope you guys have a good start to your semester, and I'll see you at our next Zoom. Thanks so much. Bye bye.